Hello. I'd like to mention briefly the next 2 months' talks. November 17, Aaron Lee from UC Berkeley, he's going to give a talk called Ending the Dark Ages, the Universe's First Stars. The universe a billion years after the Big Bang was a much different place than today. Theory predicts that stars were hundreds of times the size of our sun on average. This talk will compare the formation of stars today with the formation of the very first stars. In December 15th, which is well enough away from the holidays that I hope you can come, Greg DeLory, UC Berkeley Space Sciences Laboratory, gives a talk on water, water everywhere, from Earth, the Moon, Mars, and beyond. Water, which is essential for life as we know it, is an important indicator of conditions on other planets and moons, and so he will discuss results from recent space missions. So that's in November and December. It's always on the third Tuesday, so you don't have to remember the date. I'm very, very happy for tonight's speaker to join us. I asked him, I think, in February. So I'm really pleased. He's going to talk about our moon, from formation to asteroid target, message for life on Earth. He collected fossils as a child in Michigan and then went on to study geology at Michigan State University. And he then completed his PhD at MIT. He was assistant professor of geology at Northwestern University and now teaches geophysics at Stanford. His area of expertise is in planets and habitable environments, and he collaborates with NASA on topics related to life on Earth and other planets. He's currently studying the aftermath of the moon-forming impact. Dr. Sleep appreciates working at this time in history to conduct research on the origins of life, and he says it's like putting together a jigsaw puzzle with some pieces already known and some that are speculative and some that have new aspects. Tonight's talk, he will discuss the present Earth-Moon system, how it was formed, and how the Earth came to be habitable. Researchers believe the Earth's moon was formed by an impact of a planet-sized object smashing into Earth. The atmosphere then was opaque and a vast magma ocean devoid of life. Tonight we'll learn more about the moon's development and influences, and he will also discuss the appearance of the first forms of life and its possible origins. Join me in welcoming our speaker for this much anticipated talk, Norman Sleep.
Thank you. I'll get this started here. I have to click on this. And now we have to get this started, and I just click up. Is that on the right thing?
That's it.
Okay, we're started now, and I'll also get the pointer here. And I've worked with a fair number of people. I've just put up 4 recent ones here, and we'll get the first slide here. This is the Mare Orientale, where you can only see a little bit of it from the Earth itself. This is the last large impact basin, so it's the best preserved one. The moon is covered with craters. The Earth, how many people have been to O'Hare Airport in the last couple years? O'Hare. Did you see the impact crater? That's my point. There's no sign of it. It's resting a impact crater probably about that size or so, size of the pointer. It's eroded, covered with sediments, and we don't see a single trace of it except for the persistence of geologists. And I came to MIT in 1967. I quickly found out I'd wandered into an orchard of plate tectonics full of low-hanging fruit. The moon program then was Apollo. It was run by PIs. The senior faculty were gone. Sink or swim for the graduate students are left to run plate tectonics on their, not completely on their own, but a fair bit on their own. And basically you had, even to attend the Lunar Science Conference, you had to have permission of a PI and so on, particularly in the geophysical end of it. It was hard to publish under your own name. I came from relatively modest circumstances and made the decision to work towards plates. In the middle 70s, where I'd actually got a job by then, NASA realized that it was coming into an era of low funding, that running the planetary program like a private club was not a good idea for that reason, and it was also not a good idea because the original principal investigators were not going to be active forever. There were efforts to get people that had been involved in plate tectonics going. There was a big one called the Basaltic Volcanism Conference. Basalt's the black rock that comes out of Hawaii. There's large amounts of it on the moon, like filling the center of this crater, filling over here, large amounts over here. It was something they could, because it was known to exist in the solar system, they could center the project on, but pretty much did all of Earth, all of planetary science, got people interacting. There was also a small program on Mars. I was interested in the areas of the Earth like the Canadian Shield, the eastern U.S., where not much happens geologically, so I wasn't particularly bothered with Mars, where things go on at a pretty sedate place too. And the reason the moon is cratered is that over the last 3.75 or 3.8 billion years since this is found, almost nothing has happened internally geologically, unlike the Earth, where it is extremely difficult to find any rocks at all that are of that age. So I got involved with the moon originally simply because it's an asteroid target. It was far enough away from the Earth very quickly, by about 45 Earth radii, that one body shielding the other was negligible. You could ignore it in a calculation with just a trivial error, but they're close enough together by the size of the solar system, the same bodies were coming. So that nothing is steering the bodies. The moon is small. The Earth is large. It's like a woods full of drunken hunters. The deer is likely to get hit than the rabbit. And the same there. And so I was interested in calibrating it. We'll go through some things here that are known about the moon. This was not known until actual rocks were brought back, but it was known very quickly, very early in the Apollo program. The first Apollo landing sites were actually planned by people that believed that these were volcanoes and not impact craters. There's a very great thing at Earth science to have uniformitarianism. It was okay to a point. You don't start invoking magic to explain things, but you do have features that form extremely quickly. The Golden Gate out there probably formed during a glacial low stand. The Sacramento used to go on and go out into Monterey Bay. There's a small pull-apart basin from the San Andreas Fault where the 1906 earthquake started just offshore from the Golden Gate. This produced a canyon, produced steep drainage, and at full flood in a glacial winter probably, or maybe a glacial spring from all the snow melting in the Sierra, the river topped its levees, cut the Golden Gate, and the Sacramento went out to the Farallon Islands. After that, and it goes out here rather than go out. Remember, the sea level would be about 100 meters there, so there'd be land all the way out to the Farallons. The river would cut that and cut the Golden Gate. The How many people have been to Niagara Falls? How many people have seen the whirlpool? That again is a feature that the river was eroding back on the falls. The falls hit the whirlpool sandstone. They can basically take out with your hand. It's never been lithified. And the huge whirlpool there in the river went 3 kilometers back again, probably within a day or so. So things can form fast. These impact craters form minutes with the end of it being over in an hour or so. And there's a prejudice against this, and people wanted them volcanic. But after a little bit of data, the moon having a low density was well known. The core is about 370 kilometers radius. It's about 2% of the mass of the moon. It's quite small. The mass of the core of the Earth is about 33%. So it's tiny, but the rocks that were brought back, as I'll get to in a little bit, are depleted in elements that go into iron, and thus they have all seen making of a core. We take isotope ratios. A big to-do recently about somebody finding the moon rocks, there's 3 isotopes of oxygen, 16, 17, and 18. The 17 is quite rare, and so it's harder to measure, but crudely, the change in 16 to 17 is going to be half the change in 16 to 18. You actually have to use logarithms, and the numbers are slightly different. But if you do all 3 isotopes, plot up the normalized to 16, you'll find that until very recently, people said the moon was exactly the same as the Earth. There's a very slight difference. It's more a tribute to being able to measure precisely than the moon really being different. People will do titanium or something that doesn't particularly become volatile, and the moon is also similar to the Earth. The moon is extremely dry. At any element, you don't usually think of manganese as being volatile, but at these temperatures, basically temperatures of molten rock, manganese will condense somewhat after silicates condense. Anything like potassium that's more volatile is extremely depleted in the moon. And again, as I set up here, the mantle of the moon and the crust of the moon show the elements that should have gone into a core are extracted, and the core of the moon is too small to extract a lot of these elements. So these were kind of known early in Apollo, and people tried to come up with explanations for them, and there have been explanations since then. Okay, this goes back to George Darwin, that the Earth was spinning extremely fast. It became unstable. One of the forms of the theory is the core of the Earth suddenly formed with iron, suddenly reaching the melting point and all going to the center, which, like an ice skater pulling in her arms, will spin much faster. It turns out that this will not eject a moon, that at the time of George Darwin, people weren't able to make the calculations. The other thing is you can capture another object that's already formed. You have a very weird object. You have objects like, or has a very small core, has way too little iron in for any object that's secreted as small and medium-sized and large asteroids on its own. So you have one weirdity there. And the other thing to capture, you has to come in at exactly the right trajectory. It's like hitting a hole in one where you've never played golf before. And the composition of the moon makes it like hitting a hole in one on the par 5 by having your ball bounce 5 times in the road, go up in the air, hit a seagull, and drop in the hole. It's possible, but highly implausible. The current theory is an object that's basically Mars-sized that I'm going to call Theia collided with a Venus-sized object. Proto-Earth and Tellus get used. It kind of has the net effect of these. We end up ejecting material from the mantle of the Earth. We end up partially capturing some, maybe a tenth of Theia, into Earth orbit, while the rest of Theia will end up in the Earth. So it kind of has chemically the effects of both of these, but it's something that can be physically modeled, and it's shown to be feasible. Okay. If I'm interested, going to switch back to the moon. It's just a recorder, a passive asteroid target once it formed. The moon-forming impact vaporized and melted the Earth. It rendered the Earth totally uninhabitable. So if we're worried about asteroids that are going to reduce habitability, we need to start counting after the moon-forming impact, which is we count on the moon. We're by definition doing that. Asteroid impacts, again, because nobody was steering the asteroids. And again, the Earth is going to get hit with more asteroids, and statistically with bigger asteroids than the Earth. And we need to try to see when this threat became mild enough. It becomes very interesting for the biologists, where you decimate life and only leave high-temperature organisms in the subsurface. This can create a bottleneck for life. And many, I'll get to at the end of the talk, many of the organisms on the Earth appear to descend from organisms that were once thermophile. Okay, with the chemistry, we're to trace elements here. We have elements here. They're called moderately siderophile. Siderophile, it just means iron-loving. And you have, this is the bulk silicate Earth versus a meteorite standard, unfractionated meteorite standard. And you have ones here that are around a tenth or so. And you'll get about that abundance in the moon also. And this is just equilibrium fractionation. The mantle of the moon has seen iron at some time in its existence, and the core of the moon is way too small to bring these down. You have other elements here that are around or a little bit below 1%. And these elements are very close to having the same ratio rather than moving around somewhat here. And there's way too many of them in the Earth for fractionation with iron, and we wouldn't expect everything to fractionate the same way.
Can you say a little bit more about what do you consider iron-loving?
There are elements that will dissolve in iron rather than dissolve in rock. They're extremely trace elements like gold. Gold, if there's molten iron around, will go into the molten iron rather than going into a rock. This is something that can be measured in the laboratory, and the equilibrium ones will be scattered all over the place and somewhere down here at the bottom of the page. This is a log scale. So we're getting well over 100 times more in the Earth than we expect from equilibrium. Is that helpful? Okay. And this looks like a mechanical mixture. You mix in a component that has a composition meteorites. It doesn't seem like a lot, but the Earth is huge. It would be equivalent to dumping a 5 to 20 kilometer layer of meteorites on the surface. And of course, in the last 4 billion years, the Earth has gone round, it's convected, it's had plate tectonics, so everything is pretty thoroughly mixed in. There's subtle differences in here that geochemists could get involved in, but the message here is that these are almost the same ratio. If we take sulfur, selenium, and tellurium that are trace elements that are similar to sulfur. The ratio would be, rather than 1%, like 0.5%. So we can get other ones up here that are slightly different, and these are probably volatile. There'll probably be less of them in a meteorite mix. This is all well and good, but the moon kind of got gypped. You have all these craters on the moon, but the total mass, you add up the craters, there's excellent gravity of the moon. There are no really hidden craters. By the time the crust formed of the moon, it's basically been hit much less than the Earth has. This is a big difference here. It's something we need to explain. And these are by definition meteorites that potentially could endanger life because the Earth will become habitable sometime after the moon forming impact. They get called a veneer because people are used to thinking in the layer. There are two end-member solutions here. One, the deer and the rabbit in the woods, all the masses in a few large, almost all masses in a few large objects. The Earth is going to statistically get hit with these. We can invoke conditional probability that the moon is still there. So one of these kind of 6 or 10 large objects would statistically not be likely to hit the moon. The moon has like a 75% chance or so of surviving. This is well and good. We happen to live on a planet that survived, end of story. And again, we have about 6 in here that are big enough, boil the oceans, sterilize the Earth. So the Earth would not become inhabitable until these large impactors are used up. We can get a second solution here, and that these are iron-loving elements. The planet Theia would have a core. It would be highly unusual if it did not have a core, and we get a small fraction of Theia's core mixing into the Earth rather than going and immediately mixing with the core. And a plausibility on that, the moon has a core, has a small core, but the mass of the core, and there's also excess iron in the form of oxidized FeO, and the amount of iron you need to bring in these elements and the amount of iron you need to form the core of the moon and the FeO of the moon are comparable. They're kind of known to within a factor of 2, and within that slop they're the same. If you're just bringing in the equivalent veneer to this for the Earth, again, the Earth is larger, has more gravity, so it's going to get like twice as much equivalent thickness. It's basically the surface area, the cross-sectional area, pi or 4 pi r squared. If you're just doing proportionality, it doesn't matter which one you do. And you might probably, but not certainly, get one that will get very interesting to biologists. It would only leave high-temperature organisms living a kilometer down or so on the surface. The ocean would boil off or become hot saline water where it's hotter than a pressure cooker, which would sterilize stuff at the vents. But stuff that's a kilometer or so down in areas of relatively low heat flow would probably survive. The organisms would survive, they would multiply and beget and do things like that, and they'd eventually reach the surface and recolonize the Earth. And so we have very different indications here that these impacts on the Earth were terrible, or they're bad, but that's somewhat benign. Okay. Earth, we would like habitability. We'd like to find out when it's habitable. We'd also like to find out what the conditions were like when life would start on the Earth. Possibly we don't need to do this. Possible Mars was open for habitation, probably did not have any impacts that would sterilize the planet, and life had water, large lakes, if not seas early on. It was perfectly habitable. And it's possible that rocks got knocked off of Mars by asteroid impacts, came and some of them seeded the Earth. Does not have to be particularly efficient. Like we get like 100 Mars rocks falling into the Earth every year. So many billions have come in. It doesn't have to be an airplane with a first-class compartment. You just need a few organisms to come from Mars. And it's ironically more testable than life originating on the Earth because the Martian record exists. It's just hard to get at. We have people heard today on the news where they found a zircon that may have organic carbon in that's 4.1 billion years old. You have this one zircon that you could barely see if it was between your fingers. That's the only interest of life we have before we actually get rocks at 3.9 or 3.8. And there's just one of them. They had to go through vast piles of zircons to find it. And it has the right isotopic composition for carbon that's gone through the photosynthetic cycle. But we just have one of them. While on Mars, the Martian meteorite, that there were features in that people were considering possible fossils. Probably the magnetite is the only one that people take seriously now. This is well over that age, and it's never been heated above 40 degrees centigrade. And while you, probably in Antarctica, you can find things that have not been that hot, never been down, where you have glacial tills that are tens of millions of years old, but you would not be able to find anything even 200 million years old on the Earth that's not been heated to that. So the record is good, and we have the, what might have been organisms to begin with has been basically turned to graphite. So we're not going to be able to do DNA. Okay, the moon-forming impact, and the theory was developed. Raman Knupp has done much of the Earth. We get an impact here of two bodies. The impacting material from the impacting body is in red. Material from Tullus, the target, is in blue. Material gets scattered off. We basically very quickly, within hours, condense in Earth. We have heat from tides as the disk starts to condense in the moon. The energy, gravitational energy for the material mechanically condensing reboils. The material's repeatedly boiled off and actually cannot condense into the moon for something like 100 or 1,000 years. The projectile core in most of the models mostly ends up in the core of the Earth. As the models have got to better resolution, little bit, a few percent, exactly what we need, and some of the models will come off and end up in the disk. And the fate of the iron, once it's in a disk, is extremely poorly resolved. We're dealing with a couple percent of iron in there, but it's still big enough to make an object larger than the asteroid, a Vesta that's made of iron. It's probable iron moonlet will condense because it's more dense and the silicates condense around it. But there's plenty of time here for material repeatedly being boiled and condensed for the iron to chemically equilibrate with the silicates in the disk. The moon is 98% silicates and 2% iron. Okay, we have the core here. We're getting material here in the moon, and the material ending up in the Earth. And the moon-forming disk for this to happen, you have to have more iron than oxidants. And oxidants here, the abundant ones would be water from the oceans of the two bodies, and also ferric iron, which will act with metallic iron to make ferrous iron. And while the Earth, for the platinum group elements, which if there's molten iron around, they'll go right to the core, we had to have the mantle oxidized at the time where there was excess oxygen, and we were able to, the metal that got mixed in small droplets got oxidized. Platinum is extreme trace element. It won't, unless it gets in iron, it's not going anywhere on its own. In this case, the big message is made is that the platinum group elements, this veneer component, is telling us about the moon forming impact. It's not telling us about the asteroid target at all. So we have plausibility arguments here. People are studying these with trace elements, and I cannot give you a conclusive answer one way or the other. We could get decision trees, but you get decision trees where you're forced into properties like how oxidized the two bodies were and so on, but you don't run into anything that's an absolute stop. The dynamics is good enough to inform the geochemistry. Geochemistry is good enough to inform the dynamics, but neither of them are good enough that they could really say that this is what's going to happen mechanically. Okay, the moon is formed. Now it's moved off a bit. It's up. I'm skipping a few thousand years of history here. And the atmosphere at first would be radiating probably at the temperature of a brown dwarf or a red dwarf star that have silicates in their atmosphere. But very quickly, the silicates would condense, and we would end up with an atmosphere that was full of water and full of CO2, and will be full of some other goodies on the next slide. The next thing is that the atmosphere, that CO2 is not particularly soluble in lavas, that the bulk of their CO2, like 100 atmospheres, Venus-like conditions, will end up. But remember, they were farther away from the sun than Venus is, so that it will be fatal. It will make the Earth uninhabitable, but it won't make it permanently uninhabitable like Venus. And I'm going to get into a little bit of subduction here. This sounds like an oxymoron that we have to have rapid subduction of old plates, but I'm going to argue that the plate tectonics was not particularly fast on the early Earth, but when it did get going, it went really fast. So I'm having to switch back and forth here. This is a model of the composition of the atmosphere. It's mostly water and CO2. The water will form clouds. There are sulfur species in here. There will be sodium chloride clouds. This particular model did not distinguish between potassium and sodium. What we'd have there, and you'd have various sulfur species. You would have chlorine species. You'd have the halide up in the atmosphere. The atmosphere would have various layers of clouds here. It'd be more like a giant planet. But if you're only worried about heat balance, you only have to worry about the top of it. It's water clouds. It will basically radiate comparable to the heat that radiates now from the top of the Earth's atmosphere. And if we're worried about the precise time, we'd have to precisely know that temperature, but we can do pretty well. See the surface here at 300 K, you'll have sufficient rock vapor near the surface. The top of the atmosphere is radiating at a much lower temperature, and you'd have to get much higher temperature over here before this axis, this will curve up to where it's radiating like a star, where basically the heat produced on the inside is balanced by the heat out. This is an object passively cooling, so it's like putting your coffee when you came here into a thermos bottle rather than having it in a tin cup. You already have so much heat in the coffee, but it takes a lot longer to get out of the thermos bottle if it's blanketed. And we're down here basically comparable to the temperature that clouds the atmosphere of the Earth radiates. The atmosphere will be opaque to thermal infrared. And the heat loss here depends on the fourth power of the absolute temperature. So you pass very quickly through these, and you spend a long time here in the blanketed state where the surface is basically at the temperature of fully molten rocks, and then partly molten rocks down here. Okay, it's relatively easy to calculate a thermal history. We know the kinetic energy of the impact. Everything after a few hours is converted to gravitational energy, eventually to heat. We know the solidus and liquidus mantle materials. We compute the temperature here at the base. There's cooling here at the no moon, saying the moon got injected instead. That the advection is if there's more angular momentum, and energy and angular momentum are lost to coupling of the moon's orbit to solar tides. So we add the one here is the moon. So the relevant thing here is these models come out around 10 million years. More careful ones like come out around there, but kind of the relevant time scale to condense the atmosphere to the point where we have liquid water at the surface from here on out is on the order of 10 million years. It's long. The moon moves out slowly. Moon moves through resonances. The blanketing, the atmosphere is controlling the loss of how fast the heat can get out, and heat can only get dissipated as fast as it can escape. There's a feedback between the interior of the moon, of the Earth, how partial molten it is, and the tides. A fully molten rock has a viscosity like orange juice or less, or even water. It doesn't dissipate tides in a body that large. You need kind of a partially molten mush to dissipate tides. And if you dissipate too much tides, the mush melts, and that kills your dissipation. So it's an equilibrium process. The moon's orbit is controlled by the climate, that is these clouds that surround the Earth. You're not used to a climate controlling planetary orbits, but this is a case that happens. Geochemical heterogeneities that can, from short-lived radioactive elements, form early. There was solid crust very early on, 10 million years. Basically, the absolute time cannot be resolved. And the water and the CO2 will mostly escape to the surface. We'll have an ocean, and we'll have a CO2-rich atmosphere. And again, here is the end. We've gone through the 10 million years fairly quickly. We'll have an atmosphere that's 500 K or 200 sea level, around 100 bars of CO2. And this is uninhabitable conditions, and the CO2 needs to be subducted. And the key here for the origin of life is that the Earth cannot become habitable until the CO2 is subducted. So massive amounts of CO2 are going down the tubes in subduction zones at the time, and this is going to affect the chemistry of arc volcanics like Mount St. Helens, that rather than tapping a slab that's relatively CO2 poor, it would tapping a slab with all the CO2 it could take. Okay, just a little bit of plate tectonics here. The mantle is very hot at that time, so the material coming up melts a lot. It forms a thick oceanic crust, like the present crust off of Iceland. Ocean crust is made of basalt. It's buoyant. It's hard to subduct. But once subduction starts, the basalt here turns into eclogite. You can find some up here on the other side of the bay. And it forms what was low-density minerals, goes into high-density minerals like garnet, and the material suddenly becomes more dense, and the subduction starts real fast, drags more crusted here until we use up the old crust. The young crust hits the subduction zone. Doesn't hit everywhere at the same place, same time. The Earth is a sphere. This overall rate could be low, so the Earth could have gone through a temperature minimum at the end of the magma ocean, and then because cold material sinks to the bottom, the hot material is convecting at the surface. We use up the hot material while cold material is sunk, so the Earth could well be colder and then gradually heat up by radioactivity with plate tectonics going on, but relatively sluggish. You've probably seen in freshman books that the rate of tectonics was really fast. This was before neutrino detectors that can detect the radioactivity in the mantle, and more accurate geochemistry. The mantle is not particularly radioactive, and so it could kind of heat up 100 degrees C. We don't need very rapid plate tectonics to get rid of heat from an enormous amount of radioactivity. So I'm going through a fair bit here, but the key is that if we send down the slab rather fast, these are for the modern Earth. If you, this is the hot slab would be one that's going, that's very young oceanic crust, like up at the Juan de Fuca Ridge. You have other slabs here are slow. We don't get hot enough to drive a lot of carbonates off. There's water present, so some carbon dioxide goes into solution. These are just stability diagrams, and as you get to these intermediate pressures, carbonate minerals tend to become less stable. But you can see even with the hottest slab on the modern Earth, we're not extensively using carbon. In the Aegean, the battle would be hotter, and we come in here and we tend to lose carbon and have it come back if we had a hot slab. If we rapidly subduct, so it doesn't have a chance to heat up, old ocean crust that's had a chance to cool, this obviously has to be done episodically because we have to conserve the area of the Earth. We could still get material down, and the key here is that we can get CO2 down, but we're still partly melting very CO2-rich slabs. The atmosphere, here we have stability of various minerals. Calcite is stable. This is dolomite, magnesite, which occurs over on the other side of the bay. Iron carbonate. The greenhouse equilibrium curve is here. All these are down on this side of the greenhouse. If we're on the greenhouse side, any exposed rock will tend to form carbonates. Bicarbonates are up here. We don't possibly have enough CO2 pressure to form a bicarbonate ocean. And the question here is, does this material persist in the mantle of the Earth? That we could see material that was highly carbonatized. There are claims that it's been found, but they have not ever held up. And the other thing here is mass balance. We could put about 30 bars of CO2, 30 atmospheres equivalent, into the global seafloor. We need to subduct the global ocean, kind of crudely the surface area of the Earth 4 times. And if the rate of plate tectonics is slow, this is going to take a long time. So it's possible the Earth did not become habitable until the late Archean, but we're dealing with a lot of uncertainties, including how much CO2 was in the atmosphere to begin with. With regard to habitability, the sun isn't as bright then. You could all join the Tea Party then and not particularly bother. We could have 25 bars of CO2 in the atmosphere and it's still habitable. A few atmospheres of CO2 would still be clement. The ocean pH would change, so shelly organisms and stuff that live in the ocean now would become extinct. There'd also be no oxygen for them to breathe then, so it'd be hard for the Tea Party to talk and make comments on this. But basically, you pass through this thermophile stage first, and then a clement stage with kind of a very dense CO2 atmosphere. These depend on internal processes and may take millions or tens of millions of years. So both of these are possible states for the origin of life. It's a shopping list for the biologist. We get to 3.8 billion years, jump of 300 million or so, and not much between friends. We have black shales then, turbidites from mud flowing down continental margins that occurs like off here. We have banded iron formation, which forms from photosynthesis that takes ferrous iron to ferric iron. We have a full sulfur and carbon cycle, probably by organisms that use sunlight to take sulfide to sulfate. We also have organisms that will take the dead organic matter and the sulfate and turn it back to CO2 and sulfide. There's limited information that the pH of the ocean and these banded iron formations from rare Earth-type elements is around their differential solubility depends on the pH, and we get near and we probably, by then, most of the CO2 has gone down, and we probably have near modern CO2 in the air. That still be unpleasant. It would, there would be no oxygen in the air. The surface might have some photosynthetic microbes on it and some organisms that eat them. There'd be no ozone, so things would have to be living a little bit under the rock or evolve things to shield themselves from the ultraviolet. It takes very little rock to do that, so it's not just a little bit of translucent rock will kill the ultraviolet, and organisms live a little bit deeper down in the water column and so on. It's a nuisance. We'd get badly sunburned. We brought along oxygen, we'd get there. So again, summarizing this and kind of a shopping list here, we have the ocean at a pH of around 6. This is just a simple chemistry like the ocean acidification with the modern burning of fossil fuel. We have serpentine vents at pH 11, and people have worked on that. The idea is that you have travertine-like white smoker chimneys. These exist on the modern Earth. Any organic matter formed at depth in these highly reducing waters would get caught there. The lipids would get caught on the edge of the pores. Eventually, they trap other biological material. You get RNA world, go into DNA world, the last common ancestor. One of the food sources is hydrogen plus CO2. There'll be a little bit of carbon monoxide. This is not good for us in a garage, but it's extremely powerful food for microbes. The microbes that will eat this on the modern Earth. The organisms here are basically imprisoned in the chimneys. Chimneys will collapse every time there's an earthquake. stuff will get stirred up as dust, spread around. They can find another chimney. Lots of chimneys near the ridge axis. Anyway, the rock is more rich in minerals that will form serpentine than it is now. And the bacteria and the archaea in this hypothesis, we belong here in the archaea, are two different cell membranes where the organisms manage to escape the chimney and be able to move out. And at least no organisms with the ability to live like this have been found. Probably not surprising, since it's pretty precarious existence where you can get out and people yell jailbreak, you do it. Okay. We have geochemical evidence of deep mantle processes here for the geologists in the room. You have melting going down through much of the depth of the mantle. The cooling before we condense the ocean, we have a brief period of time that we have are forming fluids. We have the same basic pressure that we have at the bottom of the ocean, same pressure that we have in relatively shallow ore deposits, same range of temperatures, and we may fractionate platinum or something. There's no real evidence of this happening yet. That we should get things that should be preserved, should be in the mantle, but they may have got so mixed and so diluted we can't find them. Okay, the strategy of the biologist kind of comes from the other end. They have to look at something that stinks when it dies. And the strategy here is to find conserved features, deduce the early environment, and particularly rather kludgy features that the ATP, the energy currency in the cell, is basically made by a mechanical engine, which is extremely kludgy. This is something that you expect to be done with catalysts and enzymes. You wouldn't need a mechanical engine to drive the process, yet it's there. So that's something that they will focus on, and the people with the hydrotherm, the white smoke prevents that the original energy is coming from the difference of pH 11 to pH 6. This is enough energy to support modern organisms, even though there's apparently nothing that lives off that now. But there are other reactions that are that feeble in energy that life does use. The other thing is here we have to, the Earth is so affected by life. The lava coming out of the mid-ocean ridge, the lava coming out of Hawaii, we can all see, mainly in the trace elements, there's not enough stuff gone down to production to affect the major elements heavily, can see evidence that biological materials have been subducted into the mantle, and the whole mantle is contaminated with it.
What is the image you have shown?
This is at the Cedars. It's north of the Russian River. Hydrogen gas and calcium hydroxide brine are coming out of serpentine. The water has no CO2 in it because the CO2 has already been either eaten by things that will eat the CO2 and the hydrogen, or it's formed carbonate minerals. But the minute it hits the air, you get mixing, and CO2 will plate out. Sorry for not pointing that out. And then this is a land environment, and there are people that prefer this land environment. I'll get into reasons for that in a minute or two. But you have to vet anything on the Earth to see whether it's really could be prebiotic. Like somebody wanted to know, was using ruthenium as a prebiotic catalyst. A lot of the ruthenium comes from biological oxidation of sulfides. This is not a metallic where there's a trace amount of ruthenium in the sulfur mineral, like the fool's gold type mineral. And Once it's oxidized, it will form the metal. Okay, sulfur's oxidized, but the ruthenium is not. You also apparently get some cases where it's not. This is a trace element. It may be well and good. Life does use tungsten as a biological mineral, which is quite rare. It apparently does not use uranium to any extent. It's radioactive, but our bodies are full of potassium, where potassium-40 is also radioactive. So half-life is long enough, it's not going to kill a microbe. And the job of the geologist here, this job of the biologist, from here, likely environments, vetting environments given by the biologist. A very pruned tree of life here. We have prebiology, RNA world here. We have first cellular organism. And the one tree I discussed just a minute ago, the cells would form sometime in the RNA. Luca would be down here, the last universal common ancestor. We could have extinct lines that transfer genes. We have archaea here. Anything in red is thermophile. So this idea of what is that life originated in a hot environment, which is kind of difficult. You're fighting all kinds of things where the thermodynamics is the wrong way. Life evolved, colonized the Earth, large impact, zapped it, and then that was the end of all the life that there. So we had bacteria survive. We had the last common ancestor of archaea and eukarya. Eukarya may branch into here. You can see our close relatives here, animals, fungi, and plants. The macroscopic organisms are all up here, all very closely related. We're eukarya. This sometimes gets called neomura, which I didn't put on here. New wall, to tell it that the cell wall is different than bacterial. That may not be the order that went. The ceotich lavas are going to be rich in potassium and sodium. The mineral azurine is going to form. This is a ferric iron in here for you people that recognize minerals. The iron that was ferrous in the lava gets pulled out as ferric iron. This sucks the oxygen out of the lava, and we end up with something that's very reducing. As it cools, we get graphite, we get hydrocarbons, we get other goodies. We all so point out here that cells, this is pretty well known. If you weather this, you'll get potassium-rich water, whether you do it in fresh water or in the ocean. We could have this on land or ocean. Question here what the ocean composition whole is, since we don't know where the original life resolved. And this highly alkaline volcanism really doesn't return until much later in Earth history. We get tremendous amount of it early on, and then not much of it later. So the peralkaline just means something that has lots of potassium and sodium in. You get this when you melt the salt. This has been done in the lab. This is just a glacial scene in Alaska that the CO2 has been pulled down, so where we get mountains in the Archean. And again, the message here, the other message here is these brines, that ribose, the fundamental backbone to make RNA and DNA, is stabilized in this environment. It'd be stabilized by borate, which we're likely to get, molybdenate, which is less likely, but also in these very alkaline brines, sodium silicate is soluble. It's like detergent, like strong detergent, and this will stabilize ribose. Advantage for an island arc is a tectonic environment. You get all kinds of rock types here, like in the San Francisco Bay area, up in the Cascades. There's no oxygen around, so hot springs do not turn into acid sulfuric acid. And on land, you have freeze-thaw, wet, dry, water. And this has been heavily promoted, also promoted as a way of getting life on, from Mars. That Mars is much drier than the Earth. And the message here is that our DNA and RNA, the A, G, C, T, and U, are tolerant to UV. If you evolve early life at the bottom of the ocean, this is like a buggy whip holder on a modern car. It's not of any use. But if the organism, there are other equivalent compounds that do not like being around where there's ultraviolet light. We also have zinc sulfide and molybdenum sulfide. These will form in the vent. There are electrotrophic organisms on the modern Earth that can live off an electric current. There are photoelectric organisms that can camp out on these minerals and live off the small voltage that happens when the sun hits it. You don't want 1,000,000 volts, that's going to zap the organism. You want just these small fraction of a volt that allow them current. And the idea is that the nascent life, that these natural currents that were present wherever these minerals are sticking up, there's no oxygen around, so they stay around until they get buried, which will have more of the minerals in. And this is something that can be eaten. And this is one of the arguments for land. We have land and chemistry in here, and they're at least partly, but not totally, disjoint. Reminding you on the early Earth that by the time we hit any rock record, life has evolved, it's had photosynthesis. We're up into the branches of the tree of life, not near the bottom anymore.
So, how long after the collision was this happening?
Probably by 4.1, when we get the first evidence of photosynthesis, we believe that single zircon. Problem is we have no geological record, and we really cannot, they're biological clocks. They work when you have the two ends calibrated in the geological record. They do not work well when you don't have the end at the start. Things are going to evolve very rapidly at the start because they're going to be quite kludgy. They're kludgy. The first thing, you're going to get a clean origin of life probably because life is competing with non-life. Once you hit a threshold where the organism can store its genetic code faithfully, can reproduce and gather energy, reproduce and disperse. Once you cross that threshold, you're going to have, it's going to occupy every suitable environment. And every time you get one of these biological innovation bottlenecks, like the bacteria and the archaea evolving cell membranes in the scenario I just gave you, there's going to be very rapid evolution when that happens, that the organisms are going to disperse, they're going to find themselves in different environments, the evolution is going to be fast, and then it's going to be slower, and really we can't tell 3.1 from 3.3. Just using that, there's not a good way to do that, but we have a pretty firm nail in here that we have photosynthetic life by that time. Yes?
What you were saying before about life living off of electric current,
Yeah.
would that then be a good basis for saying that a modern computer is a life form?
Probably not. It could, if they were if it could self-run the factory and assemble itself without human intervention all the time, probably. But it becomes a matter of semantics. But it could become a self-replicating automaton. But it really isn't now. It could print out on your screen, please build more computers, if it's programmed to do so. Okay, one message in here is that the Earth's crust has been completely recycled except for these few zircons, definitely all of which that have been found. I could fit in this glass, probably fit them in a thimble. And we have various rocks here from the mantle of the Earth. And again, it's just basically all you can examine are trace elements and isotopic ratios. And we still have much of the periodic table that's not been fully done. Okay, Moon and Earth, and the history is tied, and I've been using the Moon partly as an asteroid target and also using the formation of the Moon to get at the starting conditions for life. I'm just going to very quickly jump up to 250 million years ago, the great dying at the end of the Permian. 95% of shell-bearing organisms go extinct, 75% of land animals. We'd like to have a relatively quick extinction mechanism where there's no time for evolution to act, no time for things that don't like it here to go elsewhere, and there's no time for the rocks on the Earth to buffer the chemistry of the ocean and the air. They're the vast Siberian flood basalts that cover if they erupted in the United States now, they cover it to like a kilometer depth. The rocks underneath, many of them are sedimentary. They're thick coal beds. The organic matter will get heated up slowly. That's going to drive off a lot of carbon dioxide, but not all in the same year. The basalt itself reacts like the rocks I showed you in the other picture there to form calcium carbonate, so it's actually a net sink. But when lava goes into coal, it will erupt, and tuffs, rocks that have formed from mixing of lava and sediments are extremely common at the base of the section in Siberia. And the key here is that when you have thick coal beds, the basalt will mechanically tend to go into it just like a magnet. If you heat coal up to around 470 degrees C, especially these are young volatile rich coals, it's just right after the coal deposits have formed, these coals will turn into liquid coal coke. That's a viscous liquid. It has about the same properties as the andesite that came out of Mount St. Helens and blew up, except it's less dense, so it'll come up even faster. And you get these big coal beds that have 1,000 cubic kilometers, trillion tons of coal in, more than the industrial reduction. These big flows, when they erupt, come in and have trillions of tons of basalt. You get this into that, and if the coal bed is offset, the sill kind of sends, where it works mechanically to anthropomorphize it a bit, sends out probes, and it'll find the next coal bed. So you can get, the coal will come out, it will catch fire, the plume will go up in the stratosphere. That's rather easy to compute. You have thousands of these going off at the same time. You go from basically nuclear winter with the sky, particularly in the northern hemisphere, filled with ash. The fly ash has been found in both Canada and Vietnam. The uranium that's come out of the coal has been found. So it's very likely that this event occurred. It's just whether it's the main thing that causes the extinction. And there's not a big literature on coal doing this. It's been known not to heat up volatile coal since like the 1780s. or you'll blow up your coking plant. So there's just kind of a small literature on how to fluidize these coals by heating them up. So you get a mixture of coal and basalt. The red coal doesn't conduct heat very well. It erupts, and there you have plenty of material for a wick. There'll be lightning anyway. It's going to catch fire. There's not enough here to use up the oxygen in the atmosphere, but there's enough to greatly increase the CO2. And if it comes out fast enough, it will kill the CO2 in the mixed layer. This is just igneous rocks that mingle, but it's the same idea. The physics of this, and you get about a 50-50 mixture that's volatile rich, low density. It's an exact mixture for an explosive volcano. And this is the hypothesis. I'm going to skip to this. And basically it's something that's under a study now, even though it didn't make the new Cosmos series to some extent. Unlike trilobites, we're not burning coal at our own volition. The trilobites had calcite eyes that dissolved in the rapidly acidifying ocean, which blinded them to the problem.
This is not the case, I think, that the volcanoes in the Siberian crust are going off for well over 100 years. Is that correct?
They went off for almost 1 million, but the big fall, it would be early on where the coal hadn't been turned to graphite already. But one of these big flows might last a year or 10 years. There's not that precision on it, but it wouldn't take long to come out. There's like trillions of tons of lava. Thousands of cubic kilometers if it helps more. It's kind of impossible to visualize that much lava. When we get in these thick coal beds, it's known that coal mingles with basalt, but the places in Siberia are covered with kilometers of basalt, and one of the most worthless things that can be mined is a mixture of coal and basalt. It is completely worthless, so there's no effort for the miners to find any more of it. There's a name, Yama in Hindi for it, J-H-A-M-A. If somebody speaks Hindi here, can pronounce better than I can. But that's the only language I found a specific word for it. Okay, we'll cut things off here. Open it to questions. I hope I took about the right time.
Thank you for your presentation and thank you for your life's work. I confess that I'm not an astronomer or even an amateur astronomer, and so the question I want to ask may be considered.
Don't worry that I'm not a professional astronomer either.
I would like to ask this. Did this collision with which your remarks began,
Yeah.
did it have the effect of tilting our Earth and setting it spinning?
Probably, but we don't know for sure.
I see.
We don't know how much the Earth was spinning beforehand. It would set it spinning, but it'd be spinning like at a 6-hour day or something at first. And then the moon goes out. It's like the ice skater spreading her arms. That you conserving angular momentum. And the astronomers have realized that you could couple with the sun too, so the Earth might be spinning closer to 4 hours rather than 6 at the start.
But the tilt, of course, is a particularly tantalizing consequence or effect because the tilt gives us the seasons that we have.
The moon also stabilizes, is exactly the right size to stabilize the tilt. If it was too big or too small, that it'd be like Mars where the tilt would move back and forth. It'll do it over hundreds of thousands of years. The other thing it left us with exactly the right amount of water, the oceans, that we get shallow seas. And that's probably a sampling bias because we evolved from organisms that crawled out of shallow seas. So you should find yourself living on a planet where it's easy to get lots of shallow seas. Yes? I'll do the other moons first. The one that's well studied in the solar system is the Pluto-Charon system. These objects were undifferentiated before the impact. They accreted out slowly enough out far from the sun that they hadn't fully melted. There's enough heat in the impact to melt Pluto. Again, we're melting water and not rock, so it's easier. And the same mechanism would form the moons of Pluto. It's far from the sun, so the solar tides do not disrupt the outer satellites where those would fall into the Earth. The tides dissipation has not moved the moon out as fast to pick up the outer moons as the moon on the Earth. We have oceans and stuff on the Earth that are very good for dissipating tidal energy and moving the moon out. And the Earth question was how many atmospheres does this have? It would have the rock vapor atmosphere at first, which would condense to this very hot CO2 and water atmosphere. That would go to this ocean with a pressure cooker-like, hotter than pressure cooker-like, oven-like CO2 atmosphere where it would have a significant amount of water and mainly CO2. That would condense and we'd go down to less and less CO2 to what finally became habitable. The CO2 would mostly get subducted. We have a nitrogen-rich atmosphere, probably more nitrogen than now. That nitrogen does get subducted. The nitrogen we're breathing has all probably been subducted, gone through organisms and come back. So on the scale of hundreds of millions of years, climate is buffered by nitrogen, but this is much too slow to act now for global warming. And then oxygen would build up and probably hit a peak at the time the coal was deposited, and then maybe reach 35% or so, and then come back now. But we don't have precise ways of inferring it. People have written curves. 1.85 billion years ago, I did mass balance of the sulfides of the seafloor, solubility, ocean circulation type, to get there's like 0.1% of oxygen in the air then. But these things are not well known. We've gone through several different atmospheres, but exactly how many is kind of a matter of semantics. It's very gradually. You're all welcome. Thank you very much.
A certificate of thanks for being here. We appreciate very much.
Okay.
What a way to talk on the moon. Thank you.
You think I hope I was comprehensible. With a fourth grade class